But the downside is that you have to pay a price. You're not testing directly quantum superposition, but you're testing collapse models. The plus side is that they're much easier to perform because this noise is there all the time, even if you do not have a superposition. So if you have a superposition, the noise collapses superposition. But if you do not have the superposition, the noise still induces a diffusion on the system. So you do not need to prepare a superposition to test the noise and to test collapse mode. And in fact, they are much more effective in testing non-interferometric experiments are more effective in testing this. So there are three strategies that have been employed with non-interferometric experiments. So one is to apply to cold atoms. So you take a cloud of cold atoms, you make it very cold. So basically the cloud shouldn't move. But if there is the collapse noise there acting on the cloud should expand a bit. Then you see whether the cloud expands or not. If it doesn't expand, nothing happens. If it doesn't expand, the collapse models are wrong. If it expands, again, let's see why. Or you take charged particles. If you have a diffusion is an acceleration diffusion. So if the particle accelerates, a charged particle, it's radiation. But all particles in life, in real life, electrons, protons, forget about neutrons, are charged. So you should see some faint, very faint electromagnetic field coming out of matter because the matter is shaken by this noise. And Catalina probably will say much more about that in the talk. Or you can take a cantilever. Cantilever, it's basically an harmonic oscillator. And then if you cool the harmonic oscillator, it should more or less stabilize in the ground state. But if there is this noise, it will not stabilize in the ground state. It will still oscillate, and then you can check this oscillation and see what happens. Okay, so we use the second type of experiments. So the emission of radiation was used to test and actually rule out the Aushie-Penrose model, at least in the easiest formulation. So you can still fix the model. So and again, I will say something quite much very quickly because perhaps Catalina will talk about this also later from the experimental point of view. So we did the theory part of the story. So in the Aushie-Penrose model, if you remember, it collapses when the correlator is given by the Coulomb potential. The 1/r shape. The 1/r shape is always problematic because when you make integrals, they diverge. So if you have point-like particles, so you have to fix the problem by making particles extended over space, a little bit extended, not much. So you have a cutoff R0. So this model actually has a parameter, a free parameter that you want to test. If the smaller the parameter, the stronger the effect, the stronger the collapse. So if you make an experiment, you do not see anything, then you are putting a bound on this parameter, an upper bound, a lower bound, sorry. The parameter R0 cannot be too small because again, the smaller, the stronger the effect. So what is the size of R0? So what does the theory says about that? So you have to guess some number. Penrose and Aushie suggested two things. So Penrose suggested that they should come, from a mathematical procedure which goes through the solution of the Schrödinger-Newton equation. I do not want to talk about that, but the moral is that each physical system has so to say, a natural value of R0. An isolated system, an isolated atom has a value of R0. An atom in a crystal has another value of R0. It's computed depending on the physical system. But there is a well-defined algorithm to compute it. Aushie instead originally suggested that it has a defined value. So every particle has a defined value independently of whether it's isolated or in an atom or whatever. This original idea of Aushie was later abandoned. Okay, so we try to test this model, again, to test the noise, to test the effect of the noise as emission of radiation. So we computed the photon emission. And here you have, in the box, you have the number of photons per unit frequency that should come out. And you see basically in the formula, I don't want to go too much into detail. You see basically that all the constants that should be in the game are there. So capital G, gravity, because it's a Aushie-Penrose model, the electric charge, because we are talking about photons, for example, and then N and N sub A basically is a way to measure the number of protons. So it's the size of the system. So the larger the system, the more photons should come out. As you see that you see R0 in the denominator. Again, the story I told you before, the smaller R0, the stronger the effect. So the more photons should come out, and then the rest I do not want talk about. Their technicalities not relevant for the present talk. Okay, so there is a theoretical prediction to first order in perturbation theory within a certain range of validity and so on and so forth. And okay, so I want to speak about the experiment because I'm not the best qualified person to talk about it. It's a technically challenging experiment with the germanium crystal in the Gran Sasso laboratories in Italy. So from right to left, you have a picture from above the laboratories, a picture inside the laboratories, and the schematic of the germanium experiment. Here you have the experimental data, which have been analyzed by the experimentalists from the group of Catalina, and then this is the outcome. The outcome here you see the lower bound. So the green bar tells you that all values of R0 up to some number between 10 to the minus 11, 10 to the minus 10 meters is excluded by the experiment. R0 cannot take that value. The point is that if you apply the prescription of Penrose to the germanium crystal, R0 should be below 10 to the minus 11 meters. So that value is excluded. So the original idea, so the moral is that the original idea of Penrose implemented in the DP model is ruled out experimentally. Again, I don't want to speak about natural ways out from the problem, but you have to make the model richer than the model that was presented so far. So what about the CSL model? The CSL model story is more difficult because there is a wider range of possibilities for the collapse. So there are two parameters first, RC and lambda, and there is not much is known about that. GRW and Adler suggested two completely different values for lambda, which are some 8-9 orders of magnitude separated from each other, and basically, and they are the black points in this exclusion plot. And then, so the gray area is a range of value which is excluded by the requirement that these models are effective at the macroscopic level. So if you require macroscopic objects to be localized, then the values cannot be too weak. And then the green area is basically these weak values which make the models useless. And then the question is how to bound from above, or hopefully one day to see something. So far, no one has seen anything so far. And so you can only exclude values of the parameters. This is the state of the art, and I'm going towards conclusion, I think. Yes, with the interferometric experiments, so experiments with atoms, experiments with molecules, experiments with crystals, and all the colored regions are values of the parameters which are excluded because the experiments proved, verified the quantum superposition principle. You see that the white area, which is the unexplored area, includes a large number of orders of magnitude of parameters. With non-interferometric experiments, instead the situation is much better, as I mentioned before. So with cold atoms, all the orange area is gone. With again a photon emission with spontaneous photon emission, the purple area is gone. With optomechanical systems, so here is a gravitational wave detectors, so large optomechanical systems, the right area is gone. And with mesoscopic optomechanical system with cantilevers, the middle area is gone. And then with several updates. So this is the state of the art about testing collapse models. You see that, I mean, much have been excluded. But now the game becomes interesting because now you have a finite region which you want to focus and to see whether really there is a collapse of the wave function as predicted by the CSL model, or whether the model basically is ruled out and one has to seek for an alternative. Okay, so I'm at the end of my talk, so I want to thank my group and the funding agency. And thank you for the attention.